Hello and welcome. I'm Simon and this is Fabrice, and this is our talk about converting scene data to dots. So I'm going to try and give a little bit of context on what we mean when we talk about this conversion workflow. So about a year ago, we built the Megacity demo, and that was really the first time we proved the scalability of dots and the scalability of the workflows for building scenes. So quick recap, Megacity is like 100 subscenes. So 100 pieces of the levels are in separate GameObject scenes. And these are then converted into entities. So the way this gives us scalability in the editor is that we only modify a small subset of those subscenes. So the subscenes can be either open or closed for editing. When they're closed, we use the efficient entity representation, and only if they are open for edit, we use the GameObject representation. So let's talk about why we want this conversion. So we basically have two different sets of data. We have the authoring data and we have the runtime data. And they are very, very different. So in the authoring data, you have hierarchies, you have every object has a name, and there's all sorts of information in there that we don't need at runtime. So if you look at the right side here, that's the runtime representation of the data in Megacity, right? So you have those 4.5 million objects. They are without any hierarchy in them at all. And we just couldn't work with that many GameObjects. So let's talk about when this conversion happened. It used to be when we made Megacity. We basically had these subscene monobehaviors, and converting them happened manually. So you would have to go in and press the Rebuild Entity Cache button, and that would then generate the efficient entity representation of that subscene. That got somewhat problematic because you make a change in some prefab. Which scenes do we need to rebuild? So the good news is, with the next release of dots, we're removing that, and we're introducing automatic importing of the subscenes. So this is using the new on-demand asset pipeline, which means that we can import the scenes in the background as you continue to work. So that's only happening for the closed subscenes. So the workflow is you make a change to a prefab, it will start importing all the scenes that use that prefab, and they will then pop in when they're converted. Now that's great because you can continue working on your open subscenes while this importing is happening in the background. So again, it used to be that when you had an open subscene, the entity representation was gone. We were running only the GameObjects at that point. But with LiveLink, we also have live convert, which means we live convert all the GameObjects to entities as you're making changes. So then everything is running as entities. Now, Fabrice will walk us through some code examples of how this conversion actually happens.
Thank you, Simon. So now we'll look in practice at how you can use this conversion workflow. And to do that, we wrote a bunch of samples, and we've put them all on the GitHub repository. You'll find the link to this GitHub repository at the end of these slides. So I will not go exhaustively over the whole code, but I will only point the parts which are really relevant to the conversion. So starting with the simplest possible example, which is almost trivial, but will still be a good opportunity to introduce a few important concepts. Just your classic Hello World equivalent for Unity, a spinning cube. So if we were making this only using GameObjects, what we would have is something like this. So we create a Unity scene. You have the default camera, default light, and then we create one cube, so just a cube primitive. And if we wanted to spin on itself, we would just have to add a mono behavior to it. And this is what this mono behavior would typically look like. Just the rotation speed as a field, and then the actual code that does the rotation inside the update function. So just one quick remark here is that mono behavior tend to be a mix of data and code. In ECS, we have a very strong separation between the two. And so the whole point of conversion is really to carry the data over from the editing representation to the runtime representation. So I will only focus on the data here. The code is not much more complicated than that, but just written in a system instead of in a callback like here. All right, let's start converting this sample. The first thing is to have something to actually trigger that conversion. So we are going to create a subscene and move our cube inside the subscene. So everything which is in the subscene will be converted, and things which are outside of it won't. So in this case, the camera and the light will just remain GameObjects inside the runtime, inside the game, and inside the editor if you're using this conversion workflow to simply guarantee good performance when you're working on a large scene like Megacity. That's also a very, very convenient way of progressively transitioning to dots, because we would like to reach a point where just everything can be converted to dots, but we're not completely there yet. So this simply allows you to keep the things which are not ready for dots yet outside of the subscenes, and all the things which are inside the subscenes. So you still have all the benefits of scalability on the things that matter. So a subscene can be open, in which case what you see are the game objects, and the subscene is just like one node in the hierarchy, the parent of everything it contains. Or the subscene can be closed, in which case you only see the root node of the subscene, and the rest is now entities. So they don't show up in the hierarchy view, but they still display in the main render of your editor, so you can still work in context. Everything is still there. It's just that you cannot click on something and have its inspector show up. For this, the subscene needs to be open. And this is how we made Megacity, and this is even more than that. This is what made Megacity possible, because if you have all these buildings open at the same time as game objects, you have over 5 million game objects in there, and that simply doesn't work. So in this case, you would simply open the buildings that you want to work on. You still see the rest of the city around you. You modify whatever you want to modify, then you close them down. They turn into entities. They are now efficient to render again, and then you work on something else. So a bit more details. Here on the left side of the slides, I've put the open subscene, so the game objects, and on the right side of the slide, I've put the entities. So the game object, and in this case, I'm back to the rotating cube example. The game object will contain a few components. So the mesh renderer, a transform, and the rotate mono behavior that we have created. So when you close a subscene, or when the conversion happens, you will simply have every single one of these components which somehow converts. So the mesh renderer, this is handled directly by the entities package. It will turn into a random mesh, which is like the equivalent in the hybrid renderer. The transform is just a little bit more complex than that, because it will not turn into one component, but in a set of 3 components. So you have the position, a vector, you have the rotation, a quaternion, and then you have a local to world matrix, a 4x4 matrix. And every frame, because the cube is dynamic, every frame you have the transform system, which is going to bake that position and that rotation into the matrix. That set of 3 components for the transform is like the default, but you can customize this. And finally, the rotate component that you just wrote, well, it will simply be discarded during the conversion. So that's a bit annoying in this case, but sometimes this is something which is actually desirable, because you might want to simply drop some information when you're doing your conversion. Maybe some things were only there to help with editing, but don't have any reason to be in the runtime. Or maybe you're making a demo of your game and you want to scrap everything which is not required by the part that you're putting in the demo. Or you're making a headless server and you want to discard everything for rendering and so on. So there's a purpose to this, and that's the default behavior. But if we want to carry it over, well, we have different options. But the most convenient of them all is something that Lucas Meyer introduced yesterday during the keynote. It's this attribute at the top of my ECS component here, which is generate authoring component. So as I said here, it's coming soon. You'll get this in the next version of entities. And so if you download the samples that we made, you'll see that we are not using this because we wanted to have these samples compatible with the current version of the package. If you have this component, this attribute, though, you can just have this. The component will simply generate an authoring component that you can attach to the GameObject, and so the same data will just carry over to entities. Good. But in this case, you would have the rotation component designed for editing, so in a representation which is easy for just the content creator to reason about, let's say degrees. And if we just carry that over, we also have degrees on the right side in the runtime, which is not ideal when it comes to the transform system, because the whole transform system works with radians. So that's a trivial example, but just to illustrate the principle. In this case, it would be nicer if we could have degrees on one side, but then radians on the other side. So for this, we could have a custom transformation here in the middle, a custom conversion. And for this, we'll need to write just a little bit of code. So I will walk you through this code. But first, there's another thing which is interesting in here, which is that our rotation will just be an angle, a rotation angle around an axis. But the rotation component here is a quaternion. So every frame, we will have to multiply the angle by the delta time. Then we will have to generate a new quaternion, multiply the quaternion, normalize to avoid drift, and so on. That would be much easier if we could directly change an angle there, directly change an Euler angle. Well, it turns out that in the long list of components that we have and that you can use to customize this transform pipeline, you can also add an Euler XYZ component where you can just add to the angle and it just works. So now, the component that I want to have in the ECS, on the ECS side is this. So it implements iComponent data, and it contains my value in terms of radians per second, so the machine optimized version. Then I will have a rotate authoring component, a mono behavior in this case, that I will attach to my game object, which has to be converted. And on this one, I will store my angle as degrees per second. Then I need to specify what happens when I transition from the GameObject to the entity. And for this, I will implement this interface, the iConvert GameObject to entity, which requires you to provide this function, convert. And this function takes 3 parameters. The first one is the entity. And it's interesting to note here that the entity has already been created at this point. So at the beginning of the conversion process, we just create one entity for every game object that has to be converted. And then we pass this entity to all the different steps of conversion so that each step can just customize the entity, add things, remove things, create other entities, and so on. Now, an entity is just a key. You cannot really do anything with just an entity. You need to provide it to an entity manager, which contains the actual API. And finally, we have a conversion system, which is not going to be useful for this example. It will come in handy later, so let's ignore it for now. And now we can add our 2 components. The first one, the rotate component, so which is the one at the top of the slide, where I'm doing the conversion of my angle into radians. And finally, this rotation Euler XYZ. To wrap up this example, just the system itself is also pretty simple. It just looks for everything that has a rotate component, everything that also has that set of Euler angles, and it increments the rotation. So first sample was just about introducing the purpose of conversion. You can go from one format to the other, and it's not only about going from GameObject to entities. And also introduce the iConvert GameObject to entity, which is the simplest way you can customize that conversion system. OK, next step, prefabs. So what you see here is just a spawner in the center of the screen, which is spawning projectiles, and each projectile is spawning other prefabs to create a trail. So it's a prefab that references another prefab. So that's what it looks like. Inside your subscene, you have your GameObject, the spawner, and this spawner makes reference to a prefab, projectile. This prefab, in turn, makes reference to the other prefab, the trail. And the problem is that these two prefabs are in the project. They're not in the scene. But the subscene is like the to-do list for the conversion system. This is where it will find all the things that have to be turned into entities. Since the prefabs are not there, we will have to explicitly declare that we also need these. We do it this way. The conversion process is roughly 3 stages. The first one is the discovery. It's where the conversion system just figures out the set of GameObjects to turn into entities. Next step is the entity creation. For every single GameObject, we create an entity. That's a very simple step. Last step, which is the most involved, let's say, is the conversion itself, where we are going to go over all the systems and all the functions that handle conversion. And we can customize these two things. The discovery stage, that's what we're about to do, and the conversion stage, that's what we did in the previous example. All right. So this is all the boilerplate I already used in the previous example. So you have the component that we want to create at the top, and then we have the authoring component on the lower part of the slide, the one we attach to the mono behavior. So this one is an ECS component. This one is your regular mono behavior with the convert GameObject to entity interface, and then the function that we are now going to implement. What I want to get in the end is this. A prefab in the ECS world is an entity. Even if you have several entities that are part of the same logical prefab, you will still have one master entity that contains the list of all the other entities, and that's the one we want here. Then we have the amount of time that should pass between spawns, here seconds between spawns, and we also need some sort of countdown to know when we have to fire the next prefab, and that's my second to next spawn. In the authoring component, I have a prefab, this time it's a GameObject, and I have spawn per second so that you can specify the frequency. So that's another opportunity of doing a small transform from one to the other. I have a frequency here, but I have a duration on the other side, so I'll just inverse it. OK, so writing the component itself is not too complicated. We just create one of these periodic spawner components. I set the seconds between spawn to be the inverse of my frequency, and the interesting bit is this one, get primary entity, because now we want to reference an entity which comes from the conversion of another GameObject. So we need to look into some sort of mapping table between GameObjects and entities, and this mapping table is provided by our conversion system. So the third parameter of a function here, we can say, please give me the entity that matches this GameObject. And this thing will throw an error if it has no idea what this prefab is. So we need to declare these prefabs. And that's how we do it. Another interface, declare reference prefabs. And then we just add this function. We add our prefabs to the list of prefabs that have already been found. So this way, our GameObject, the spawner says, I need this prefab, injects it into the list of things it converts. This one says, I need this other prefab, gets added to the list, and everything gets turned into entities. So notice that this process is recursive. As long as you keep on adding stuff to that list, it will keep on exploring the dependencies of those new things. So, a quick summary of that second example. We've seen the 3 important conversion steps, which are quite useful to keep in mind when you want to customize all that stuff, because the order in which things happen can be quite important in certain configurations. And how you declare prefabs with this I declare reference prefab interface. OK, something a little bit more entertaining now. Conversion systems, and we've been using a little bit of physics here, just to make it look nice. I have a set of 15 spawners here. And there are two interesting things to look at in this sample. The first one is that each spawner is not only spawning one prefab, but it's randomly spawning 1 out of 3 prefabs. So you have like the red, green, and blue rigid bodies, and it will just pick one at random every time. So we have like a double indirection there in terms of prefabs. The other important part in this sample is that my 15 spawners here trigger in sequence, one after each other. And I just wanted to have this behavior, but I also wanted to have this not depend on the exact amount of prefab spawners that I have. I wanted the flexibility to add as many as I want or to have as little as I want, and the system will automatically adjust the frequency to the amount of things I have. That sounds trivial, but the thing is that if you use these conversion interfaces that I've introduced in the previous examples, you are converting one object at a time. And so you cannot really reason about all the objects that you have. What I need to do here is look at all the spawners and then decide on the frequency. So I need to tackle the problem at a different level. But first, let's look at the structure of this sample. So here I've only put 5 spawners on the slide because 25 would have bloated the whole thing. But they all reference the same prefab list. And this prefab list contains 3 prefabs. So my 3 rigid bodies, red, green, and blue. And in terms of the locations where these different components are stored, I have all my spawners which are in the subscenes. They are in the hierarchy. And then the prefab list itself and the prefabs that it's referencing are all prefabs, and they are all stored inside the project. So I need to sort of untangle that list of dependencies to provide the conversion workflow with the list of GameObjects to convert. So let's look at the authoring component. So the one that I will add on my prefabs, which are here on the left. So that thing is a mono behavior. Oh, sorry. That's the one in the middle that I'm doing here. I shouldn't reorder my slides at the last moment. So the prefab list authoring is the one that contains the list of 3 rigid bodies. And so in the GameObject side of things, it will just contain an array of prefabs, 3 GameObjects. When it will get converted, it will have to declare all these prefabs. And so here, I'm just adding that list of prefabs into the existing list of prefabs. Finally, it will also be converted. So once again, I will implement the iConvert GameObject to entity interface. And in this conversion function, I will use something that I've not used before, which is a buffer, so a dynamic buffer. Why? Just because I want to actually store an array. I'm not going to store a single component. And so this uses an interface which is slightly different. And you'll notice that the type that we use in there as the type of our array is spawner list component. And this is something which inherits from iBuffer element data. So instead of being just an iComponent data, it's an iBuffer element data. It's almost the same thing. The only difference is that this one is designed to be stored as a dynamic buffer and attached to any of your entities. And this buffer will automatically grow and shrink, but it also has a small inline storage for performance reasons. A quick parenthesis here is, why am I not directly storing an array of entities? Because that's what I need in the end. Well, the thing with ECS is that everything works with types and not really with variable and fields or variable names and so on. So here, if I wanted to have several arrays of entities, I would still need to have several different types. And so that's the whole reason of spawner list components. It's its own type, and so it identifies the array. Back to the full sample. So I'm creating a buffer on my entity. So now I can store all the prefabs. And once again, I'm calling my conversion system getPrimaryEntity to have the mapping between my GameObject prefabs and my entity prefabs. All right. now we handled the right part of this picture. Let's have a look at the left part of the picture. So the spawners themselves, we have an authoring component, which is pointing to our list, so prefab list that we just converted. And this one will only declare the referenced prefab, so in this case, only the prefab list. And as you can see, I'm not going to implement the iConvert GameObject to entity interface on this one, because, well, that's the main difference of this example. I want to handle all my spawners at once and not one by one through a function call. So, ECS, of course, we have a system in there. So systems are the way by which we just query the database of all the objects that we have, and then depending on certain properties of these objects, we are going to extract a certain list of things we want to process and process them, which is exactly what we want here. So it's a GameObject conversion system, and if you used a bit dots already, you've been using job component systems and component systems. This one is just a normal component system, but it will register itself automatically with the conversion workflow. And also, it contains a few extra bits which are related to this mapping between GameObject and entities. And I will get back to this right after. So it has an onUpdate, just like every system. This onUpdate will only be called once in this case. But, I mean, that's fine. Nothing says that onUpdate has to be called repeatedly. And here, I'm going to extract my list of spawners. So I'm creating an entity query. And this entity query says, give me the list of everything that contains a spawner authoring. Then I turn this into an array, and I will process my array. But hold on a second. There is something which is a bit weird in here. The type that I'm looking for, I'm using an entity query, which is an ECS concept, but I'm actually looking for a type which is a monobehavior. How does that work? Well, this is something that we call hybrid mode, which allows you to actually attach monobehaviors to entities. That's a bit of a strange concept, but it comes in very handy, and especially in the context of conversion here. So when I told you that you have a GameObject and it turns into an entity, that's not the full picture. There is an intermediate step, and an important one. The GameObject turns into an entity, sure, but this GameObject is in the subscene, and it contains a component. The entity, it contains a monobehavior, sorry, and the entity is in what we call the conversion world, which is this intermediate world. And you will understand why in just a moment. This spawner monobehavior is attached to my GameObject, and we will actually attach this spawner still as a monobehavior to the entity. And from this point on, we only look at the conversion world, and so we are in something that can be controlled from the ECS API, and so we can use our queries for finding all the spawners, and we'll get all the entities that match these spawners. And then the actual conversion is this last step, going from the conversion world to the destination world. And in the destination world, we will have our proper ECS spawner component. So back to this code. I now have my array. Oops, I skipped a step. This array, I can just iterate over it. Every single spawner in this array will be converted, and I will add a component, a spawner component to it. One interesting bit here is this, get primary entity. Well, previously I was using these iConverts GameObject to entity interface, and it was providing me with the entity that I was working on. I don't really have this anymore. I have to find the entity myself by looking in this mapping table, and that's what I'm doing here. So what is the entity that maps to this spawner that I'm converting? And then I add the proper components, which once again looks up a prefab and so on. So summary of our third sample. We've seen the use of dynamic buffers. We've seen that actually it's all conversion systems below the surface. The interfaces are just for convenience in the simple cases. And then we've seen the importance and relevance of the conversion world, which is this somehow intermediate hybrid world. And I will let Simon take you through the fourth sample. Thanks.
Thanks, Fabrice. So the fourth sample is all about blob assets. So might be a bit hard to see what's going on here, but what we have is a graph of 5 nodes, some edges between them, and entities that spawn at nodes choose an edge to walk at, and then go to the next node, pick a new edge, walk along that. So let's just start with what are blob assets. They are a really simple concept. It's just data. It's data that you allocate during conversion that is then serialized into your SubScene binary file. And you can have as many of these as you want. When they are serialized, they are put into one big allocation. Also, there's no serialization happening, so it's all the internal references are offset-based, so it's literally just loaded into memory and is ready to use. So zero-cost serialization is what it's all about. So let's see how we build one of these. This is our source data, because what we want to do is take the graph and represent that in a blob asset. So we have 5 nodes and some edges, and in model behaviors, it's really simple to represent that. So you just have our authoring component. It has an array of authoring components, which are the links it has. And then it has a little function to draw the gizmo for it. So you can actually pull these around in the editor and see what you're doing. We also have an authoring component that holds the prefab that we want to spawn, but Fabrice already went over that, so let's just skip through it. Now, the blob asset we want to build. Let's have a node, and let's have it have an array of integers that are which links it has, and then a position. And then the entire graph is just an array of nodes. And then the spawner just has a reference to that graph. And how many, or how long till the next one spawns, and then the prefab to spawn. Really simple. So the conversion is just a simple conversion system. So it queries the nodes. It's all the same that Fabrice did, except we have this build node graph. And that's what actually builds the blob asset and returns a reference to it. So let's look at that. Just a simple function. So the first thing we do is we create a blob builder. And you can think of this as a string builder. It's just a utility class we use to build up the blob. Then we construct the root, and we take it by ref, because we want to actually put some data in there. And then we allocate the array of nodes inside the root. And we give it the length of the array of authoring nodes we have. Now this returns a blob builder array, which is a special array we can use to put data into the blob. Then we just iterate for every node. We assign the position, and then we allocate the array of links based on the authoring links. And then we just fill in the indices. It's all really simple. And then we call create blob asset reference. And this will actually create that single allocation based on how much data has been put into the blob, and patch up all the references and return something that is really efficient. Okay, let's just look at the memory layout of the thing we just built. Now remember, a node graph is just an array of nodes. And an array in blobs is just an offset to the first element and a count of elements. So that's what we have here. We have 8 being the offsets and 5 being the number of nodes. Then we have our 5 nodes. Each node is just an array and then a float 3. Again, it's really simple. And then we just have the integers that are in the arrays in the nodes. So this whole data structure is just a small example. It's 160 bytes, if I remember correctly. But it's just really efficient to access the data. And one of the things that makes it efficient is that when we load this data, we require it not to change. It's immutable data. That means that we can access it from different threads at the same time without having to worry about doing any sorts of checks. Now let's just look at using this data at runtime. I just have a simple entities for each. And then I grab the nodes from the graph.value, which gives me back my node graph, and then .nodes, which gives me back that array of nodes. Then I can just index into that array like any other and get my destination node. Now there's one big catch here. You should not forget the refs. This is really important. What happens if you forget the refs is that you take a copy of the array. Since everything is offset-based, you will then just be indexing into your stack. This is a big cause of errors. So what we want to do is we want to make this a compile error. And we'll be working on that. We now have a hook in the compiler, so we can actually detect when you do this and trigger an error right there. But for now, please remember this. So back to our example. We grab our nodes, our destination node, and then we just do some things with it. The code here is not that important. It just picks the direction, walks along it. If it reaches the end, it picks a new link and sets that as the target. And otherwise, it just moves some distance based on delta time along. So just to summarize, blob assets, they're immutable. There's only one allocation per subscene, which makes them really efficient. Zero cost serialization. You use the blob builder to build them. They're referenced using blob asset reference. And they're safe and cheap to use from jobs. We don't have to do any safety checking because this data cannot change. Also, there is like a blob pointer, which is the same as the array, except there's only one element, so it's just an offset. And there's a blob string, which is just an array of characters. And don't forget those refs for now. I guess I can also mention blob assets are currently used for physics shape collision data and for animation data. So we are using this internally for assets as well. And that's our talk. Thank you.
For some extra info, we have the link to the talk that we gave last year at Unite about streaming and serialization, the way we use SubScenes in the Mega City demo. Here's the link to the GitHub repository that contains the samples for this talk. And coming up next in this room, you have more like the, let's say, user-facing side of conversion, a talk from the UX team. Thanks. So if you have questions, there are microphones at the back of the room.
And otherwise, we'll be hanging out at the breakout room out there for a little bit.